In this video, we will be discussing connections between the sum of the eigenvalues and the trace of a 2x2 matrix. Let A be a 2x2 matrix with the entries A, B, C, D. Prove that if λ1 and λ2 are distinct eigenvalues of A, then λ1 plus λ2 equals to the trace of A. Recall that from the definition of the characteristic polynomial, p of lambda equals to the determinant of A minus lambda times the identity matrix. This is equal to the determinant of the matrix with entries A, B, C, D minus lambda times the 2x2 identity matrix. And this is equal to the determinant of the matrix with entries A minus lambda, B, C, and D minus lambda. Recall that the formula for finding the determinant of a 2x2 matrix M with entries A, B, C, D is determinant of M equals to AD minus BC. This gives us P of lambda equals to the determinant of the matrix with entries A minus lambda, B, C, and D minus lambda. And applying the formula, this gives us A minus lambda times D minus lambda minus BC, which is equal to lambda squared minus A plus D lambda plus AD minus BC. Note that since λ1 and λ2 are eigenvalues, they must be roots of the characteristic polynomial p of lambda. If p of λ1 equals 0, then λ1 squared minus A plus D times λ1 plus AD minus BC must also be 0. If p of λ2 equals 0, then λ2 squared minus A plus D times λ2 plus AD minus BC must also be 0. Since p of λ1 equals 0 and p of λ2 equals 0, λ1 squared minus A plus D λ1 plus AD minus BC equals λ2 squared minus A plus D times λ2 plus AD minus BC. Now cancelling AD minus BC from both sides gives us that λ1 squared minus A plus D times λ1 equals λ2 squared minus A plus D times λ2. Now λ1 squared minus λ2 squared equals A plus D times λ1 minus A plus D times λ2. λ1 squared minus λ2 squared equals A plus D times λ1 minus λ2. Using difference of squares, we have that λ1 plus λ2 times λ1 minus λ2 equals A plus D times λ1 minus λ2. Now since λ1 and λ2 were distinct, λ1 minus λ2 is not 0. So λ1 plus λ2 equals to A plus D. We prove that for a 2x2 matrix with distinct eigenvalues, the sum of its eigenvalues equals its trace. In fact, for any n by n matrix A, the trace of A equals the sum of its eigenvalues up to multiplicity. So if an eigenvalue λi has multiplicity mi, you'll have λi appear in the sum mi times.